Hello, everyone. So in this video, we're actually going to discuss the other type of comparison test, the so-called limit comparison test. And this is going to involve a lot of the same steps that the traditional comparison test entailed. However, there's going to be some very large distinctions. So let's take a look at this following example, in which this following example will illustrate how the traditional comparison test doesn't quite get us to where we need to get in terms of logic, in terms of telling whether the series converges or diverges. So we're going to shift gears midway through this comparison test and invoke the so-called limit comparison test to help us out. So let's consider this example, the infinite series from n equals 1 to infinity of 3 over n plus 5. And like any other series in which we're going to invoke a comparison test, the first thing we do is try to find a series to compare to. So we take our series function, in this case 3 over n plus 5, and I always like thinking of this as though I'm squinting and asking what happens for large n, which term is contributing the most to the numerator, which term is contributing most to the denominator. So I'm always thinking large n here. And by large n, I really mean sort of as n goes to infinity, gets absurdly large. Well, in that numerator, there is just that 3. But in that denominator, we have sort of the battle between n getting larger, as well as that number 5, which is staying the same. So hopefully we can see that, well, in the denominator, that n is contributing the most to that full denominator as n gets large. So it looks as though the series we're going to compare to is the series from n equals 1 to infinity of 3 over n. So this is the series we're going to compare to. And the next step for all of our comparison tests is always, well, what does the series we're comparing to actually do? Which brings us to step 2. What does that comparing series do? Well, if we look at this series, this is where we would invoke things like the P series or even geometric series for that matter. So we take a look at the series that we're comparing. We ask, who is this series actually? And well, we can think of this one of two ways. This looks like a P series with P equals 1. And since P is, well, equal to 1, which is less than or equal to 1, this series diverges. So again, with just a P series at hand, since we have some number over an n to the, in this case, the first, that P in this case is equal to 1, it diverges. The other way we can see this is, well, this series is actually our friend, the harmonic series, in disguise if we just bring that 3 out in front. So this is the series from n equals 1 to infinity of 1 over n, which we can see is the harmonic series. So it diverges. Okay, great. So our series we're comparing to diverges. And if we think about this in terms of logic, well, the only way we could tell what our series does when comparing to a divergent series is if we can show our series is in fact larger than that known divergent series. So let's try to set up the inequality. And again, when we're trying to set up this inequality, this is under the guise of trying to do a traditional comparison test. So I'll just make that note. This is our traditional comparison test that we're trying out. And as a spoiler, we're not actually going to be able to set up this inequality the way we need it to. So again, what we're trying to show is that our series that we started with, 3 over n plus 1, we want to show that this is in fact greater than or equal to a known divergent series, which is that series 3 over n. So again, we're trying to show that this inequality is true, hence those question marks right there. And the way in which we can try to show whether or not this inequality is true is, again, just doing a little bit of algebra. So the first thing we note is we can divide 3 by both sides, and then we can cross multiply. So the question we're really asking here, again, when we cross multiply, is we now have 3 on the left. On the right-hand side, we have an n plus 1. Well, we can subtract n from both sides, and what do we see happens? Well, we're asking the question whether or not this inequality is true, and, well, if this was true, we would have 0 is greater than or equal to 1, which this statement is false. So the traditional comparison test doesn't look like it's going to help us out here. Because again, when we're comparing our series to this known divergent series, we would need to show that our series is larger than that known divergent series to say something about our series. But we're not actually able to make that comparison in this case because the inequality we tried to set up turned out to be false. So this is where we would tend to go towards the limit comparison test. So I'll just say limit comparison test. And we're still going to do this as step 3. As in, we've already established the series we're going to compare to. We found what that series that we're comparing to does. But now we get to do the limit comparison test. And the way in which the limit comparison test works is we take the limit as n goes to infinity. Surprise, surprise. But what we look at is a ratio of our series functions. So we take our original series, in this case, 3 over n plus 1, and we divide by the series function that we're comparing. So again, I'll say this is the original. And this is the comparing series. And what we want to show is that this limit comes out to be a finite number. So let's just set this up again. So we're dividing 2 fractions. So we take that fraction in the denominator and we reciprocate and multiply. So we would have here that this is 3 over n plus 1. Then we multiply by the reciprocal of the fraction of the denominator. So we get this as n over 3. And then we just take this limit the way we normally would. Of course, we can see that we can do a little bit of simplification. Those 3's knock or cross each other out. So we're really looking at the limit then as n goes to infinity of n over n plus 1. And for us with this test, well, what happens is, well, we get to do L'Hopital's rule. We get an infinity over infinity. Again, this numerator is growing towards infinity. This denominator is also growing towards infinity. So we do L'Hopital's rule. Take the limit as n goes to infinity here of the derivative of the numerator, which is 1, derivative of the denominator, which is 1. And lo and behold, after doing this L'Hopital's just once in this case, this limit turns out to just be equal to 1. So what does this mean? Well, since the limit of the fraction of our series functions as n went to infinity came out to be a finite non-zero number, both series will do the same thing. So again, in this case, since the limit of ratio of our series functions as n goes to infinity is a finite non-zero number, and I'm going to emphasize those 2 points, finite and non-zero. Both series do the same thing by the limit comparison test. So by step 4 then, we put all this logic together. So step 4, let's synthesize. So since both series do the same thing, because that limit came out to a finite non-zero number, and the fact that we showed that previously the limit that we are comparing to diverges, we know both series do the same thing, both series diverge. So by the limit comparison test, both series do the same thing in terms of diverging or converging for that matter. But since one of those series is a known divergent series, both of them must diverge. And in particular, the series we're comparing to is known to diverge. So that's generally the way in which the limit comparison test works. We're going to go through other examples like this in class, but the things to point out is we see the utility of the limit comparison test in that it helps us out when we try to set up an inequality and we can't get that inequality to work out the way that we want. Like in this case, where we just couldn't set up that inequality in the logical manner we needed it to. So we could invoke the limit comparison test to help us out in this case. Now, what I haven't told you so far is we don't actually need to do that previous step of trying to set up an inequality. We could go from step 1, determine a series to compare to, step 2, figure out what that series we're comparing to does, and jump right into the limit comparison test if we wanted to. All right, that's the limit comparison test. Let's practice some more examples in class.